For chapter 19, make sure that you check out this little cheat sheet guide all about redox reactions, how to recognize the redox reaction, how to assign oxidation numbers, and most importantly, balancing our oxidation reduction reactions. So these steps are going to be key when solving problems. We want to assign oxidation numbers first, separate into the oxidation reduction half reactions, and then balance each half reaction using the following steps. First, balance all elements except the oxygen or hydrogen. Balance oxygens by adding water. Balance hydrogen by adding H pluses. Balance charge by adding electrons. And electrons go on the right for oxidation, the left for reduction. If it's a basic solution, you have to do one additional step. For every H plus, you add OH to both sides. Combine the H plus and the OH into water. Cancel out any waters that appear on both sides. And now you have the balanced reaction. All right. Multiply the balanced half reactions so an equal number of electrons are consumed and produced. Add the two half reactions together, and then clean it up. Combine any identical substances and reduce coefficients to the lowest terms. Make sure that atoms and charges balance. And here's a few tips on balancing equations. Let's look at number 1. All right, we want to balance the following equation for both charge and mass. So I wrote, we've got copper Cu going to copper plus 2, so that's an oxidation, right? Oxidation is losing electrons. If you lose electrons, you become more positive. And I went from 0 after I assigned an oxidation number because all elements as is are, in their natural state, is a 0. So 0 to a plus 2, that's our oxidation. And Ag plus to Ag solid, which is its natural state. So going from a plus to a 0 is reduction. Okay, so we're going to divide it into our two half reactions. Our copper to copper plus 2, and we have our Ag plus to Ag solid. So there's my two half reactions, my oxidation, my reduction half reactions. All right, so it's in my 2. I'm going to, in order to go from copper to copper plus 2, my 2 electrons go on the right because 2 negatives and 2 positives gives me neutral. And on the left, Ag plus 1 electron, so a negative and a positive gives me my neutral Ag. Now notice that I have 2 electrons on top, 1 electron on the bottom, so I need to multiply my bottom by 2 to cancel out my electrons on the left and the right. So that would give me 2 Ag plus 2 electrons plus 2 Ags. I'm going to combine the two together. So I'm just going to drop everything down. Cus plus 2 Ag plus to yield Cu plus 2 plus 2 Ags. Let's look at number 2. When the following equation is balanced properly under acidic conditions, what are the coefficients of the species shown? So I've got H3AsO4 plus Cu, yielding HAsO2 plus Cu plus 2. Okay, I'm going to assign oxidation numbers to everything. My copper, this is my easiest one. Copper, just as is 0. And over here, copper plus 2. So I must have lost electrons to go from 0 to plus 2. So that's what's being oxidized. So we're just going to assume that my other species is what's being reduced, but we still need to assign oxidation numbers. Hydrogen is always plus 1. Oxygen is always minus 2. So to figure out what As is, I'm going to figure out the rest of the charge of my compound. So 4 times negative 2 is negative 8. 3 times positive 1 is plus 3. So negative 8 plus 3 is -5, so AS must be +5. Now let's see what it is over here on the right. Again, O is always -2, so 2 times -2 is -4. H is always +1, so that's +1. So -4 plus 1 is -3, so AS must be +3. So we went from AS having a +5 oxidation number to a +3, so it's been reduced. I'm going to write down my 2 half reactions. Copper S solid on the left to copper +2, so it's been oxidized. We have our H3ASO4 being reduced to HASO2. Now, I'm going to rewrite this here. So my first one, I'm going to balance my copper. I need to add 2 electrons on the right. Right? 2 negatives and 2 positives gives me my neutral on the left. Now my reduction, I don't have a charge that I have to worry about, but I do have to balance my AS and my AS. Okay, they're good. I need more oxygens on the right. Notice I have 2 O's on the right and there's 4 O's on the left. So remember our rule. To balance oxygens, we need to add water. So on the right, I need 2 waters because I need 2 more O's. Okay, so right now on the right, I have 2 O's plus 2 O's is 4 O's. 4 O's, 1 AS, 1 AS. Now, I need to balance my H's. Remember, to balance H's, we're going to add H+. So on the right, I have 4 H's plus 1 H is 5 H's. On the left, I have 3, so I need 2 more H+'s. Okay, so we're balanced as far as H's, 3, 4, 5 H's, 4, 5 H's, 4 O's, an AS and AS. Now we need to balance charge. If I have 2 H+'s, I need 2 electrons on the left. That's 2 positives, so I need 2 negatives. Then we can combine them together. Notice what's great. I have 2 electrons and 2 electrons, so they're going to cancel. So let's see what we're left with. We're just going to drop down our copper plus our 2H plus H3ASO4. Bring down everything else on the right. Cu plus 2, HASO2, and 2 waters. And I think we should be good. Let's look at the rest of the question. Water appears in the balanced equation as where is the water? It's as a product with a coefficient of 2. And that should, which element is oxidized? Who's being oxidized? Well, we said our copper was being oxidized. Our copper went from 0 to +2. Oxidation is losing electrons. Let's look at number 3. When the following skeletal equation is balanced under acidic conditions, what are the coefficients of the species shown? We're also going to have a little end addition, and I'm going to say and basic, just so we can see what happens, what we do different if we have basic conditions. Okay, so first I want to add my oxidation numbers. We know O is always -2, so 4 times -2 is -8. What must S be to have an overall -2 charge? So S must be +6. All right, we know O is always -2, H is always +1, so let's figure out what C is. This would be -8, that would be +2, so that'd be -6. 2 times +3, so that would give me +6. Okay, plus 1, negative 2, so 3 times negative 2 is negative 6, plus 2, so that'd be negative 4, so this must be plus 4. And then negative 2, so that'd be negative 4, this must be plus 4. Okay, let's look at who changed from left to right. My sulfur went from plus 6 to plus 4. So it's been reduced. Let's see what happened to my carbon. Carbon went from plus 3 to plus 4. It's been oxidized. Okay, so let's write each of these half reactions. I'm going to write my oxidation reactions, so I have I got to write my whole species. H2C2O4, and on the right I have CO2, and the reduction is SO4, 2 minus, and then on the right I have H2SO3. Now remember, if this is what's being oxidized, then it is also the reducing agent. So whatever species is being oxidized, it is the reducing agent. Whatever species is being reduced is the oxidizing agent. Okay, first we need to balance our elements first before hydrogens and oxygens. So I have 2 carbons on the left, I need 2 carbons on the right. All right, the second thing I need to do is look at my oxygens. I have 4 oxygens on the right, 4 oxygens on the left. Great. I have 2 hydrogens on the left, so I need more hydrogens on the right. Remember, when I need to add hydrogens, I have to add H pluses. Okay, so we're good there. And now I need to balance charge. I have 2 pluses on the right, so I need 2 electrons on the right. Now my charge is balanced and all elements are balanced. Let's look at the reduction. I have SO4, so I have 1S, 1S. Okay, I have 4 O's on the left, 3 O's on the right. So I need one more O on the right. Remember, when I add oxygens, I have to add water. Now I have 4 O's. On the right, I have 1, 2, 3, 4 H's. So I need 4 H's on the left. So 4 H pluses will be added. Now I need to balance charge. I am neutral on the right, so I need to be neutral on the left. I have 4 positives, a 2 negative, so I only need 2 electrons on the left, which is great because when I want to go to add all of this together, 2 electrons on the left, 2 electrons on the right. Good, let's bring everything down. So I have H2C2O4 plus SO4 2 minus plus 4 H pluses. 2 CO2s plus 2 H pluses plus H2SO3 plus H2O. Okay, is there anything that can be reduced? I see one thing. I have 2 H pluses on the right and 4 H pluses on the left. That can be reduced. 2 and 4 can reduce. I can get rid of 2 H pluses on the right and 2 H pluses on the left. So I now have a balanced equation. This is my final balanced redox reaction. And I believe it says water appears in the balanced equation as it's a product. Yeah. With a coefficient of 1. Now what if, like I said, I wanted to make this in basic conditions? There's one more step if this was in basic conditions. I'm going to add OH minus to both sides to get rid of any H pluses there are? Well, notice here I have two H pluses, so I'm going to add two OH minuses to both sides. So, let's see where that gets me. 2 H pluses plus 2 OH minuses makes 2 waters. Okay, so I'm going to bring down everything. H2C2O4 plus SO4 2 minus plus those 2 waters to give me 2 CO2s plus 2 OH minuses plus H2SO3 plus H2O. Can anything reduce? And we would look at this and go, oh, I have 1 water on the right, 2 waters on the left. So that can reduce. Get rid of 1 water on the right, get rid of 1 water on the left. So just go from 2 waters to 1 waters. Now this would be our basic conditions. Basic, there's hydroxides. Acidic, there's H pluses. Next, we're going to refer back to question number 1 and write the cell notation for the balanced reaction. We're going to draw a picture of the cell and we're going to label all the parts. Okay, so think back to what this looked like. We had our oxidation was the copper going from Cu solid to +2. So oxidation is losing electrons. Oxidation is where the anode is, or we can say at the anode, oxidation is occurring. So both start with a vowel. That's one way you can help remember it. Then we also said reduction was where reduction is gaining electrons. So we went from a positive to a neutral. So our silver is where reduction, again, reduction and cathode, that at the cathode is where reduction is happening. They're both consonants. Okay? So we know that oxidation is losing electrons. So the oxidation number increases. Reduction is gaining electrons. So our oxidation number is decreasing. The oxidation agent is the one that's being reduced. It's the electron acceptor. The reducing agent is the species that's oxidized. And here's how we would draw what this looks like. So, like I said, we start with our anode. Our anode's on the left. And so we show our oxidizing going from copper solid to copper +2. And we show that with a single line in between. And then we show our salt bridge, our double line. And then we show the reduction. So we went from a plus to a neutral. Make sure you show the solid, liquid, gas in parentheses. Then what this would look like is I have my beaker with my copper 2+ aqueous solution, and I have my copper anode, and over here I've got my beaker with silver aqueous solution, Ag+ ions, with my Ag, my silver solid, as my cathode. And this is where reduction is occurring. And then in between here I've got my salt bridge, and we can see that the voltage electrons are traveling from my anode to my cathode. Now for this part of the question, it wants to know which directions do the following reactions go. What is the E net for the overall reaction? Well, E net, to find our E cell, is E cathode minus E anode. And so when we're looking at this equation, we need to first figure out, well, who's being oxidized, who's being reduced, because whoever's being oxidized is the anode. Whoever's being reduced is the cathode. So we already figured out that the copper, going from copper to copper plus 2, copper is being oxidized, and the silver is being reduced. So our copper half reaction will be our anode, the silver half reaction is the cathode. Now we need to figure out what the E of the cathode is. So I'm going to flip my page to our standard reduction electrode potentials, and I'm going to find for silver my Ag plus. It says Ag plus, my E naught is 0.779, and we said our silver was our cathode. So to find our E cell, I'm going to say 0.779 minus, let's find our anode, which is our copper. So going from copper to copper plus 2, copper to copper plus 2, so be careful you find the right one, is 0.337. So we just take our E cell as 0.779 minus 0.337, and we get 0.462 voltage, and it's going to go as this is written. We want that positive value. If it's positive, it goes to the right, just as written. Let's look at the second part of the problem. We were given 2 Fe plus 2 plus tin plus 2. So if I look at from left to right, my iron goes from plus 2 to plus 3. So it's lost electrons. It's becoming more positive. So the Fe is oxidized, so it's the anode. The tin went from plus 2 to 0. So the tin has been reduced, so it is the cathode. So when finding our E cell, we need to find the value of our tin going from plus 2 to 0. So this negative 0.14 value, that's our cathode. And then we need to find the value of our iron going from plus 2 to plus 3. Here we go. Here's our iron, plus 2 to plus 3. Doesn't matter if it's flip-flopped. We're going to still write down our E naught value, our standard reduction potential value, 0.771. So if I take negative 0.14, that's our cathode value, minus the anode value, I get a negative 0.991. That means it goes to the left. It's going to be opposite of the direction that this is written. So it's going to go to the left because it's a negative value. Now for part B, it says to balance the half reactions under acidic conditions, describe how the oxidation state changes for each species. So 1, 2, 3, 4, 5 different reactions. Hopefully you've tried them on your own. I'm going to show you what I did. So to go from copper to copper plus 2, so 0 to plus 2, obviously it's been oxidized, and so on the right I needed 2 electrons. That's it. The second one, Cr2O7 to Cr plus 3. So I assigned oxidation numbers on the left. Obviously O is negative 2, so that 7 times negative 2 is negative 14. What must the chromium be? And remember, this is all negative 2, so negative 14, this must be plus 12, because negative 14 plus 12 is negative 2. And there are 2 of them, so 12 divided by 2 is 6. So I went from plus 6 to plus 3. So it's been reduced. It's a reduction reaction. And obviously I would need 2 chromiums to balance that first, right? 2 chromiums on the left, so I would need 2 chromiums on the right. Then I need 7 O's on the right. Remember, to get 7 O's, I have to add waters. So I added 7 waters on the right. That gave me 14 hydrogens. So on the left, I need 14 H pluses. And then last, we need to balance charge. So on the right, I have 2 times plus 3, I have plus 6. So on the left, I added 6 electrons because 14 pluses minus 2 is 12. So I would have 12 pluses. In order to have my left be equal to plus 6, 12 plus 6 electrons would give me an overall plus 6 on the left and a plus 6 on the right. Okay, the next one. H3AsO4 to HAS2. All right, I assigned oxidation numbers. Obviously, this is always -2, and that's always +1. So AS has got to be +5 there and +3 there. Okay, so it's a reduction reaction going from +5 to +3. Balancing my AS, they're balanced. So next I need to look at my O's. The right side needs 2 more O's, so I need to add 2 H2O's on the right. That gives my O's balance, and then I have 2 H's plus 1 H is 3, I'm sorry, 4 plus 1 is 5 H's. On the left I only have 3, so I need 2 H pluses. And because I have no charge on the left, I need to have no charge on the right. So 2 H pluses, so I need 2 electrons on the left. ClO3 minus 1 to ClO4 minus 1. So assigning oxidation numbers, my O's are always -2, so that would be -8. Chlorine must be +7 in order to be -1 overall. And -2 assigned to here would be -6, so chlorine must be a +5 to be an overall charge. So going from +5 to +7 is an oxidation reaction. And the only difference between the left and the right are my oxygens. The left needs 1 more oxygen, so I need to add water to the left. If I add water to the left to give me that extra oxygen, I have 2 H's, so I need 2 H pluses on the right. I then need 2 electrons on the right, so that they both have a -1 charge. And last, HClO to Cl2. Okay, so my Cl2 has a 0 oxidation number. HCl and O is always -2. H is always +1, so that Cl must be +1. +1 plus 1 is +2, -2 is neutral. So going from a +1 to a 0 is a reduction reaction. First I need to balance. I have 2 chlorines on the right, so I need 2 chlorines on the left. So 2 HClO. Chlorines are good. Now I need to balance my oxygens. I have 2 oxygens on the left, so I would need 2 waters on the right. That gives me 4 H's on the right. I need 4 H's on the left. I already had 2 H's, so I need 2 more H pluses. And to balance my charge, since I have 2 pluses, I need 2 electrons, 2 negatives.